Assalamu alaikum. In the first problem, you have a sphere of naphthalene having a radius of 2 mm. When you convert it into the meter, you have to divide this 2 by 1000. You will get the answer in meters. So this sphere is suspended in a large volume of still air. Air is still; it is not moving. This is the large volume. Let's assume. So this air is present at the temperature of 318 Kelvin, while the pressure is 101.3 kPa. The surface temperature of the naphthalene can be assumed to be 318 Kelvin. This is the surface temperature of naphthalene. Okay, and its vapor pressure at this temperature is 0.555 millimeter of mercury. So vapor pressure of naphthalene is 0.555. I am representing the naphthalene by A, while air is represented by the B. Okay, so in order to convert this a millimeter of mercury, because I have to make the units consistent, this is the unit in kPa, so I am converting this mmHg in kPa. So for converting, you know that 760 millimeter of mercury contained is equal to 101.3 kPa. Okay, this millimeter of mercury will be cancelled with each other and you will get your answer in kilopascal. So this is the vapor pressure of naphthalene. Okay, now the next thing is the diffusivity of naphthalene in air at 318 Kelvin is this. So diffusivity is also given 6.92 into 10 raised to power minus 6 meter square per second, and you have to find the rate of naphthalene evaporation from the surface. So you have to find the Na. Okay, I hope the problem is clear now. Basically this is the naphthalene, so it will evaporate in the air and you have to find at which rate this naphthalene is being evaporated. So in the case of spherical particles, there are two types of the cases. The case one is diffusion through a stagnant layer. So when the surrounding air is at still, there is no movement in the air, so that's why you can say NB is 0. Flow rate of B to the naphthalene is 0, while only naphthalene can go into the air. So this is the first case, but there is also another case in which there is equimolar counter diffusion, in which case NB is not equal to 0. In this case NB is equal to minus Na. So I will explain this example later. So first I am solving this example. So for spherical particles you will use this formula, but when the mass transfer from the surface to the large distance compared to the sphere surface, it says that when this naphthalene is being evaporated in a large volume, as the air is huge volume, so that's why we can say R1 is approaching to 0. So radius of the air is very high. This is R1, and we can say this R1 is infinity. So if R1 is infinity, so 1 over R1 will be equal to 1 over infinity, and 1 over infinity is always equal to 0. And the partial pressure of naphthalene at this point, at the infinite point, it will be 0, because it can't go at that point. Okay, so we are assuming that partial pressure of naphthalene at infinitely large volume, in the infinity large volume, is partial pressure is 0. So in that case Ca0 or is partial pressure, or its concentration is becomes 0. So Na, this equation can be written like this. As you can see here, it is written 1 over R1. R1 over R1 is 0. So this will become 0, and you will left with only this R0 will cancel with this. So DAB CT over R0 log of, and the other thing remains constant. So you know that concentration is equal to P over RT according to the ideal gas law. We can write like this: P over RT. So DAB in place of CT you will write PT over RT, and here you will also write P over RT. So P over RT below, and in the in below you will also write P over RT. Okay, so RT remains constant, so RT will be cancelled with each other, so that's why you are writing here only pressure, PT minus PA2, PT minus PA1. Okay, I hope it's clear. You will use this formula as you are given the data in form of pressures. Now everything you have in this formula, DAB, which is this, PT total pressure, it is 101.3. R0 is the radius of the naphthalene sphere, which is 2 mm, which is 0.002 meter. R is the value of R is 8.314 kilopascal into meter cube per kilomole per Kelvin, while the temperature is 318 Kelvin. Log of total pressure is 101.3, and the partial pressure of naphthalene at infinitely large radius is 0. So I am writing here 0. Total pressure is 101.3 minus PA1. PA1 is the initial is the partial pressure of naphthalene at the surface. Okay, so which is 0.07397. okay, just put the values. You can just cancel these units as well. This kPa will be cancelled with each other, and this Kelvin will cancel with this, and this meter square will be cancelled with this m, and you will only left with m1. So this will become meter square, the second, so per second, so that's here, and here it is kilomole, it is -1, and on the above it will become +1. okay, the answer is kilomole per meter square into second. Now the second question is, you have to calculate the rate of burning of carbon particle having a radius of 2.56 centimeter. Okay, so there is a mistake, I am removing it. Okay, so radius of the particle in this case is 2.56 centimeter. In order to convert it into the meter, just divide the 2.56 by 100, you will get your answer in the meters. So you have a carbon particle in an atmosphere of pure oxygen. This is, let's say this is carbon particle, and it is being placed in an atmosphere of pure oxygen at the temperature of 1000 Kelvin and at the pressure of 1 atm. Assuming a very large blanking of CO2 has formed around the particle. Okay, you know that when carbon reacts with oxygen, it forms CO2. So as this reaction is carried out, a blanket of CO2, this is a blanket of CO2, it is formed around this carbon element. So at the surface, at the carbon surface, this is the carbon surface here. So you have the partial pressure of CO2 1. So here the partial pressure of CO2 is considered as 1, while at this state the partial pressure of of oxygen is 0. As you can see here, the oxygen can't reach because of this CO2 being formed around here. So that's why we can say here the partial pressure of oxygen is 0. At very large radius, so as if you reach at infinite radius, let's say it is r1 is infinity, so 1 over infinity will become 0. So when you reach at infinite radius, so partial pressure of CO2, so CO2 can't reach at that point, it can't reach. So that's why we can say the partial pressure of CO2 is 0, while the partial pressure of oxygen at this place, because this whole volume is filled of oxygen. So that's why we can say here the pressure is 1 atm. Given the diffusivity of oxygen in the carbon dioxide, so diffusivity is also given. DAB is 1.032 centimeter square per second. As remember that 1 centimeter square is equal to 10 raised to power minus 4 meter square. This centimeter square will cancel with this centimeter square, and you will get your answer in meter square per second. Okay, everything is given to you. I have converted the ATM into the kPa. The 1 ATM is equal to 101.3 kPa. this ATM will be cancelled and you will get your answer in kPa. Everything is given and you have to find the rate of burning of carbon particle. So rate of burning of this carbon particle you have to determine. So in the next slide, this is the problem of equimolar diffusion. In the last problem, in the first example, he said you have a large volume of still air, but here there is no matching of still air. CO2 is being formed and the diffusion occurring in both direction, in this direction and in this direction as well. So we can assume equimolar diffusion just like this. If you have a vessel, one containing 80% nitrogen and 20% oxygen, and this vessel you have 20% nitrogen and 80% oxygen. So oxygen, here the oxygen is high, while here the oxygen is concentration is low. So oxygen will travel to this side, while at this side the nitrogen is higher, while here the nitrogen is low. So nitrogen will transfer from this side to this side. So this is the example of equimolar counter diffusion. So for this in this case we use this formula. In the form of concentration we use this expression. We know that 1 over r1 is very large, so we can put it as 0, because 1 over r1 is equal to 1 over infinity. 1 over infinity is 0. So we can write this expression like this, because this becomes 0 and this r0 will cancel with 1 r0. So you will left with r0. So this CA is equal to PA over RT. So RT is because of that formula, because of the conversion. So you will use this formula. So this is the formula I written here. So this is DAB divided by R is the general gas constant, 1000 is the temperature, while R0 which is the radius, 2.56 into 10 raised to power minus 2. I am doing this is a mistake. So PA1 is 101.3 minus PA2 is 0. So just do the calculation, you will get your answer. So I have written the units here as well. This is a unit of diffusivity, this is the unit of R, and this is the unit of radius. I forgot to write here Kelvin. Kelvin is the unit of temperature. This Kelvin will cancel with this Kelvin, and this meter square will cancel this meter, and you will left with m raised to power 1, which will become meter square. So that's why here meter square per second, here per second, and this kPa will cancel with this kPa, and you will left with only kilomole per meter square into second. This is the two film theory. In the two film theory, you discuss about the mass transfer in the two phases, gas phase and the liquid phase. So if you can see here it is the phase 1, which is gas phase. Here the PA is the pressure of bulk gas, Ca star is the concentration. Here it is written, Ca star is the concentration of liquid phase, which is in equilibrium with the gas phase. Okay, and Ci means the concentration and pressure at the interface, and Rg is the resistance, gas film resistance, while RL is the liquid phase resistance. So the formula is given in front of this, like Rg is equal to 1 over kg. Kg is the individual gas film mass transfer coefficient, while KL is the individual liquid film mass transfer coefficient. So DABG is the diffusivity in the gas phase, DABL means diffusivity in the liquid phase, ZG is the thickness of the gas film, while ZL is the thickness of the liquid film. So this is the let's say this is the bulk gas. So it is at the higher concentration. Solute A is at higher concentration at this state. It will form an interface. Let's say you have a gas and this is a liquid, which are in contact with each other. This is gas and this is liquid. So their joining point is the interface of these two phases. So this is the interface of. So when the heat transfer takes place from gas to liquid, there is a film formation around these phases, and this film formation offers some resistance, and this resistance so this film offers some resistance to the mass transfer. Okay, so mass transfer will be resisted by this film, and this resistance has this formula. Okay, while the resistance in the side of liquid phase will be represented by this formula, and at the interface the concentration is CAI and the pressure is PAI. Now this is Ca, which is the concentration of A in the liquid, and this is Pa, this is the concentration of A in the liquids. So Henry's law is also used. It says that partial pressure of A is equal to concentration of A, and H is the constant, which is the Henry's constant. It says that partial pressure of A is directly proportional to the concentration of A. Higher the concentration of A means higher the partial pressure of A. These are the different expressions used to represent this Henry law. Now, so in the case of two film theories, if you want to find the rate of mass transfer, so you use these formulas. Okay, so the meaning of every term is written here, and this KOG is the overall mass transfer coefficient based on the gas phase. So in order to find this formula, this you have to use this expression, and in order to find the overall mass transfer coefficient based on the liquid phase, you have to use this formula. So let's understand it by an example. For a system in which component A is transferring from the liquid to the gas phase. So this is the liquid phase and this is the gas phase. Let's say liquid phase is water. Let's say it is water, and it contains any component A in it. A gas is oxygen. Let's say it is oxygen or air. I am writing this just for the case of understanding. And this A wants to transfer to this air. Okay, A is any component. So for the system in which component A is transferring from liquid to gas phase, the equilibrium is given by, so this is the formula, this is the equilibrium expression, y star is equal to 0.75 XA. Okay, in order to understand this concept very clearly, you have to learn about the theoretical background of this two film theory as well. So this is the equilibrium expression, y star is equal to 0.75 XA. We can also write it, this is the Henry law expression, the previous this is the Henry law expression. So this H is when you compare these two equations, you can get H is equal to 0.75. At one point in the apertures, the liquid contains 90% A. So XA is 0.9, and the gas contains 45% of A. YA is 45. Always remember, the mole fraction of the gas phase is represented by Y, while the mole fraction of liquid phase is represented by X. So Kg, the individual gas film mass transfer coefficient at this point is in the apparatus is 0.02716. Okay, so this is individual and as well as it is gas film. So for individual you use the small k, and for gas film, so that's I am writing here G. So that's why Kg is equal to 0.02716, and the 70% of the overall resistance to the mass transfer is known to be encoded in the gas phase. So for the you have to remember these two formulas. the friction resistance offered by the gas phase is equal to the resistance offered by the gas phase divided by the total resistance of the two phases. Okay, the total resistance of the two phases is represented by this 1 over k og, while the resistance offered by the gas phase is 1 over kl. Okay, if this is an interface, so this is the gas phase resistance and this is the liquid phase resistance. And fraction resistance offered by the gas phase. What is the fraction? Let's say it is R1 and it is R2. So how will you find the fraction? You will divide the R1 divided by R1 plus R2. This is the way. So R1 and R2 is represented by 1 over kg. R1 and R2 is equal to 1 over kog. Let me write it again. This is just for the sake of understanding. 1 over kog. So fraction resistance offered by the gas phase is 0.7 and the resistance offered by the gas phase. Sorry, there is a mistake. As it is a gas phase, so that's why I have to write here kg. That was a mistake. So 0.7 into 1 over kg divided by 1 over kog. Okay, so just for the sake of understanding, this is the total resistance in the gas phase. Sorry, this is the total resistance of the two phases. This is phase 1, this is phase 2. So total resistance of the two phases kog, it will be equal to resistance of the gas phase. What is the resistance of gas phase? It is 1 over kg, small k. I am writing it by this one, small kg, plus the resistance offered by the liquid phase. So for resistance offered by the liquid phase, we use H over small k into L. It is also written here, H over small k into L. So for more understanding, you have to go into their derivations in order to understand the whole concept. For now, you can only assume, you can only have, for the sake of, so the fraction resistance of the by the gas phase will be this term divided by this term. I hope it is clear now. Now I am moving back to this. 1 over kg is equal to 0.7 of overall resistance of the two phases. Okay, kg is 0.02716. It is equal to 1 over kg is equal to 0.7 into 1 over kg. So here only the unknown is kog. You will find this by this formula. You will get it is equal to 0.019. So in order to find the molar flux of A, you will use this formula. Okay, so in this formula you don't know the YA star. So for YA star you will use this formula. YA star is equal to 0.75 into XA. So 0.75 XA is 0.9, which is given to you, 0.9. You will get YA star is equal to 0.675. This is the equilibrium concentration. So Na is equal to KOG into YA star minus YA. So KO is 0.019, while YA star is 0.675 minus YA is 0.45, which is given. This is given. The gas contains 45. So your final answer will be this. In order to find the interfacial concentration of A, you will use this formula. So this formula is similar to this formula, but these formulas are developed when you are going from gas phase to the liquid phase. So that's why this formula is written like PA minus PAI. Okay, so if you are moving from, in this example, the solute is moving from liquid to gas phase. So that's why you will write YA minus YAI minus YA. Similar is the case with this expression as well. As you can see here, KOG into PA minus PA star. So while if you go, this formula is for gas to liquid. So if you go from liquid to gas, so this expression will be reversed. It will be written like this. Now Na is, you know, Na, it is 4.274. It is equal to kg. So kg is, this is the formula for kg. YAI you have to know, calculate it, and YA is 0.45. Okay, so just divide this 4.2 by this term in order to find YAI. So 4.274 into 10 raised to power minus 3 divided by 0.027 is equal to YAI minus 0.45. Just bring this to this side, it will become plus. So it will add, when you add these two terms, you will get this answer, which is equal to 0.607. In the three part, you have to find the overall mass transfer coefficient for the liquid and the gas phases. So by calculating the overall mass transfer coefficient for liquid and the gas phase. So for gas, I have calculated it right here previously. While for the liquid, you will use this formula: 1 over KOL is equal to 1 over H into kg plus 1 over KL. Okay, you have to find the KOL. You have kg, H, but you don't know the KL. So for KL, you will use this formula: 1 over KOG is equal to 1 over kg plus H over KL. All of the formula which I am using are written here. Okay, these are the two formula I am referring right now. So 1 over KOG is 0.019, kg is 0.0276, while H is 0.75. it is from here. KL you have to find. So it will be equal to 1 over 0.019. it will become here and will be written with negative side, is equal to 0.75 over KL. So just take the reciprocal. So when you take the reciprocal, this KL will be written above, while 0.75 will be written below. So KL divided by 0.75. So just calculate, do the calculation, you will get KL. So put this KL in this expression now. So 1 over KOL is equal to 1 over H. H is 0.75. I'm using this formula now. Kg is 0.02716 plus 1 over KL. So KL is 0.0476. Just do the calculation, you will get your answer. KOL is equal to this. Now the other question is, this is not the figure for this example. Now for a system in which component A is transferring from gas to liquid. So here he has asked you, you have to go from gas to liquid. So the equilibrium is given, expression is given by this expression: y is equal to 0.64 into xa. At one point in the apparatus, the liquid contains 60 molar percent of air. Okay, so liquid, so you will write x. So xa is 0.6, while and the gas contains same amount, ya is 0.6. The individual liquid mass transfer coefficient at this point is 0.057. Individual and liquid, so I will go small k, and the liquid is for liquid I will write L. So it is given. Now he has asked you 80% of the overall resistance to the mass transfer is known to be encoded in the liquid film. Okay, so here he has told you the liquid film. This is the formula. So fractional resistance offered by the liquid phase equal to resistance offered by the gas liquid phase. I told you this was the gas fusion and this was the liquid resistance, liquid film. So for liquid resistance is equal to H over KL, while overall resistance is equal to 1 over kg. So just divide this liquid resistance by the overall resistance, you will get the fraction resistance over by the liquid phase. So fraction resistance is 0.8 Okay, so I will bring this point A to here. At this point, just do the cross multiplication. Okay, here below is 1, just do the cross multiplication. So I will write 1 over k og is equal to, so for I have just replaced their positions. 1 over kg will bring here, while 0.8 will be written below the h over kl. Okay, h is 0.64 in this case. We know it is 0.64. While kl we know, which is 0.05766. Just put the values, you will get your kog 0.072. It is written here. Now you have to find the molar flux of A. So in this case, as you are going from gas to liquid, so that's why you will use exactly similar formulas. Na is equal to kog into Pa minus Pa star. So you can see Ya minus Ya star. So just put the values. You don't know the Ya star. So for Ya star, you will use this formula. Ya star is equal to 0.64 into Xa. So Xa is 0.6. So just put the values, you will get the Ya star. Now put this value in this expression and you will get Na. So Na is equal to 0.0155. And in order to find the interfacial concentration, you will use this formula. Na is equal to Kl into Xi minus Xa. So try to remember this formula. Everything will be cleared with this. I have used Na is equal to Kl. So Kl is this. X is for liquid. This is from another book. Just for the sake of understanding, Kl into Xai minus Xa. Now you have to find the Xai. So that's why you will divide Na by Kl. It will be equal to Xi minus Xa. Bring this Xa to this side. It will be written like Xa plus Na over Kl. Just put the values. You know Xa, which is 0.6. You know Na, which is 0.015, and you know the Kl, which is 0.057. Just put the values, you will get the Xai, which is equal to 0.87. Now the last thing has been left, which is overall mass transfer coefficient for liquid and gas. For gas we have calculated, and for liquid you have to calculate it. So for liquid, 1 over Kl is equal to this, but in this expression you don't know what is the value of this Kg, so you have to find it first. So for this you will use this expression 1 over Kg, KOG is 0.072 from here. Kg, 1 over Kg you have to find, so that's why I am bringing this to this side. It will be written with minus sign. H is 0.64 divided by KL. KL is 0.0577. Just put and you will get, just take the reciprocal. So just change their position. So it will be written with minus 1 raised to power minus 1 and it will be Kg. You will get your answer. Now put this Kg in this here, put the values, do the mathematics, you will get your answer. So this is KL 0.046. Now the next thing is a weighted column is used to absorb ammonia by water from 6% in air. So you have air and ammonia which is going in. Okay, the concentration of ammonia in this air is 0.06. The flow rate of the gas is, so flow rate, which is G, it is 1.2, and the pressure is 1 atm and the temperature is 20 degrees Celsius. Calculate the overall mass transfer coefficient. You have to find the overall KOG. The data given are water flow rate to the gas flow rate is 1.4. Water is liquid. Liquid to gas is L by G is equal to 1 by 4. Outlet gas concentration is 1.5%. So here gas goes up while this water goes down. So this water takes ammonia from this stream and it goes from here. Okay, as you can see here, the ammonia concentration is high, while when it goes here, only 1.5% ammonia is left. So it is going from it is being reduced from 6% to 1.5%. Okay, the column height, the column length is 100 centimeter. Just divide it by 100, you will get your answer in meters, 1 meter. Column diameter is 2 centimeter. Divide by 100 to get it answer in meters. Henry constant is 1.3. So I am representing the ammonia by A. Now you have to find the KOG. Okay, so for KOG you will use this formula in which you don't know the WA. So for WA you will use this formula G into YA1 minus YA2. You know YA1 and YA2. Okay, and G is 1.2. Just put the values, you will get your answer for W. For area you will use this formula A is equal to pi dl. Okay, pi is 3.14, d is the diameter which is 0.02. You can write it like this as well, and L is 1 which is height. So I am writing here it is height which is length. So area will be equal to 0.062. As you have used meter in SI and this length in meters, so you will get your answer in meters. G is in kilo mole per meter, so answer will be in kilo mole per meter. So in this expression you have to find now the delta y into lm. It is the logarithmic mean of the concentration. So formula is delta y1 minus delta y2 divided by log of delta y1 over delta y2. For delta y1 the formula is ya1 minus ya1 star. For delta y2 the formula is ya2 minus ya2 star. So A star means equilibrium expression. So for this you will use Henry's law. Ya1 star is equal to hxa1, ya2 star is equal to hxa2. Okay, so you don't know about xa1 and xa2. Let's find it. For xa1 you will use this formula wa is equal to g ya1 minus ya2. You can put these two expressions equal to each other. So in order to find xa1, let's say you want to find the xa, you will bring this L to this side. So G by L into ya1 minus y2, and you will left only with xa1 minus xa2. When you will bring this xa2 to other side, it will be written with plus sign. So G over L over G is 1.4, while G over L will be 1 over 1.4. Ya1 is 0.06, it is written here, while ya2 is 0.015. xa2 is 0. I am assuming that here at this point in the liquid, water contains no ammonia. Here the water which is coming here, it contains 0 ammonia. So that's why xa2 can be assumed 0, and the xa1 will be calculated for this. Now put the xa1 and xa2 here. You will get ya1 star and ya2 star. So delta ya1 was equal to ya1 minus ya star. Put the value for ya1 is 0.06, ya1 star is 0.04173. Delta y2 is equal to ya2 minus ya2 star. ya2 is 0.015, ya2 star is 0. Your answer is this. Now delta ylm was equal to this expression. So just put the values. Delta, you know delta y1 which is 0.018, you know delta y2 which is 0.015. Just put the values, you will get the delta y logarithmic. Now the final thing is this expression. In this expression you know everything. W is 0.054, A is 0.06283, delta ylm you have just calculated it. So just put the values, you will get your answer. I hope it is clear now. Now I am moving forward. So this is the exercise question. So here he has asked you no mole fraction in liquid phase. It means XA2 is 0. Everything is similar. A wetted column is used to absorb ammonia by a water 6 volume percent. So volume percent in YA1 is 0.06. The gas flow rate is 2.1. Similar. Pressure is 1 atm. Temperature is 20. Calculate the overall mass transfer coefficient. Okay, the water flow rate to the gas is L over G is 1.3. Outlet gas concentration is 1.7. Length is 100 centimeter. Henry constant is 1.4 while the column diameter is 3. Now just look at this. Same G is some parameters are different to each other, but the problem is same, procedure is same. Just change the values in this procedure, you will get your answer. Try to do it by yourself. Now the next is so you can find the individual gas film coefficient, mass transfer coefficient, by using these expressions. Let's use this expression. In this example, he's asking you calculate the gas film coefficient for the absorption of you have to find the gas film coefficient for the absorption of sulfur dioxide from a dilute mixture with an air in a wetted wall column using Gilliland and Sherwood correlation for wetted column. Okay, gas velocity is 2.5, temperature is 293, viscosity is 1.78 into 10 raised to power minus 5, density is 1.22, diffusivity is 1.22 into 10 raised to power minus 5, inside diameter is column diameter is 25 mm. So formula for calculating the kg is this. For this you have to first calculate the Sherwood number. So for Sherwood number you will use this expression. So this expression says you have to find the Reynolds number and Schmidt number. So Reynolds number is equal to rho du over mu. Put the values here, you will get the Reynolds number. The units are in SI units. You don't have to. There is no need for any unit conversion. Schmidt number, the formula is mu over rho d. Put the values, you will get your answer. No, you know Reynolds number and Schmidt number. Put these values in this expression, you will get Sherwood number. Now put the Sherwood number here. Put the value of d, diameter and the diffusivity. You will kg. You will get kg. So this is the procedure. Now let's see another way how to solve this. So in another way, what you can do is, you know, Sherwood number is equal to kg over d into d over capital D. Kg, d is diameter 2.5 into 10 raised to power minus 3. Capital D is 1.22 into 10 raised to power minus 5. Okay, so just do the division. You will get 2049. When you divide this 25 into 10 raised to power minus 3 by 1.2 into 10 raised to power minus 5, you will get 2049 into kg. Reynolds number is equal to rho du over mu. Put the values, you will get Reynolds number. Schmidt number is, just put the values, you will get the Schmidt number. Now put this Sherwood number 2049 into this expression. 2049 into kg is equal to 0.023. Reynolds number is 3370 raised to power 0.83, and Schmidt number is 1.1959 raised to power 0.44. Divide this 2049 to the other side, just to this side, just like this. So just do the division, you will get your answer. So this example was similar to this, just the parameters are different. U is given, temperature is given, viscosity is given, density is given, diffusivity is given, and diameter is given. Just the numbers are different. You have to do the similar calculation, just change the parameters and your answer will be different.